you, Cody.
Sorry about that.
No worries, no worries. First of all, I do want to thank you, Cody, and the whole ACT-IAC Quantum group for giving me this opportunity to present. These are definitely evolving ideas, but they've been evolving over several decades. So there's some old stuff and some new stuff in this talk. And mostly what I want to talk about is this idea that wiring things together is more important than we thought. It used to be, oh, the wiring was just something that we did to connect things that actually did stuff. And now we're discovering that the wiring is the main event, so to speak. And that's very much the case in all three of these models of computation that I'm going to talk about. That's interesting. There we go. So I'm going to talk about three models of computation. So the rho-calculus, the ZX calculus, and hyperdimensional computing. And so this is the quantum working group. So you know, ostensibly I should be focused on quantum compute, and that's kind of right in the center of these. The ZX calculus is very much organized around quantum computing and has lots of applications in quantum computing. And the other two were not originally designed for that, but it turns out that a lot of the intuitions in the ZX calculus can be pushed out to those two because they're so focused on connections. So as we'll see, sort of the moral of the story with respect to the ZX calculus is it's the topology that matters. And because the rho-calculus and HDC are both kind of very topology aware. In fact, the rho-calculus, you could say, is at the very extreme of topology aware. You'll see that we can kind of pick up some of the ZX calculus stuff. All three of these models are compositional. So that what that means is that if you have, or you can make larger, more complex programs out of smaller, simpler ones, which is, you know, as engineers, we all kind of like that idea. That's not true of all models of computation, as we'll see in a moment. Two of the models, the rho-calculus and the ZX, provide notions of concurrency and non-determinism, as well as a good, crisp notion of complexity. And one, HDC, provides a natural place to do learning. So I want to tease you a little bit and say there are lots of papers out there now. You can also find some popular articles. So Quantum Magazine has an article on HDC, as does Wired Magazine. Ostensibly, those are pretty much the same article, but I would check them out sort of as a first dive, and then Pinty-Canerva's original paper on hyperdimensional computing is a good model. Before I go much further, let me say just a little bit about myself and the company that I founded, Firefly. So Firefly is coming up to its first year as a company. My co-founder, Ralph Banco, is general counsel. We have a good, strong dev team led by Jeff Turner, and we're currently actively working with Paul Snively, and hope to bring him on board in the not too distant future. We're providing high throughput networks, transaction server networks for a variety of companies, and decentralized projects, including SingularityNet. I spoke at the federal blockchain working group on some of the work that we're doing for SingularityNet, and you know how that's kind of already helping them considerably. So please take a look at that talk as well. So let's dive into some of the points I wanted to make about these models of computation. So a long time ago, I developed this table. It didn't have these two columns, and it didn't have these rows down here because they're all somewhat new, to analyze different models of computation. And there originally there were just four different properties that I wanted to look at. One was completeness. Could you say everything you wanted to say? Two is compositionality. As I mentioned, can I build larger, more complex programs out of smaller, simpler ones? Do I have an explicit model of concurrency? That turns out to be a major issue when you're dealing with computation. And then do I have an explicit model of complexity? And you know, for those people who are programming on a regular basis, when you're at the command line, you still use regular expressions. So they're quite useful, even though they're not Turing complete. They are compositional. They don't have a notion of concurrency, and they don't have a crisp, clear notion of complexity, although you can render such not too far away from regular expressions. Turing machines are absolutely complete. That was one of the first models of computation for which we, you know, it was the Church Turing thesis that, you know, that sort of gave us a sense of what completeness might mean. They are not compositional. You can't take two Turing machines and whack them together and get a third, at least not in the original model. Turing machines are not concurrent. They're decidedly sequential. They do have a good notion of complexity. Lambda calculus kind of flips this around. So they are compositional. They are not concurrent. Berry's theorem tells us that the lambda calculus is sequential. And they have a terrible notion of complexity. Beta reduction copies resources willy-nilly. It wasn't until the pi calculus came along in the 1990s that we had a model that had all four properties. And then that sort of launched this whole family of mobile process calculi. And then I studied the pi calculus extensively and found a small bug, so to speak, in the pi calculus, which I corrected with the rho-calculus. So the rho-calculus has all four properties, plus this new property, which is computational reflection. So you can turn computation into data and data back into computation. And then the ZX calculus came along around the same time as hyperdimensional computing. So around 2008, 2009, both of these were proposed. The ZX calculus is a way of thinking about quantum computing that is largely about the connections, as we'll see. And hyperdimensional computing was an attempt to be a neuromorphic style of computing, which is why it's quite good at learning. Peter Suter, for example, has papers out where he shows near real-time training, which is a marked difference from, say, the weeks it takes to train GPT or Claude or any of the other large language models. So that's it's a big change in terms of what we might do in the learning and AI setting. So I'm going to dive into the rho-calculus, but before I do that, I'm going to pour my hot water into my coffee cup. 1 second. All right, thank you for your patience. Oops, looks like it. In order to motivate the rho-calculus, I just want to make a couple of observations, sort of general observations. These are really from my own personal studies. You'll notice that if you study, you know, Western science, you'll notice that the language of classical mathematics is devoid of agency. You know, Newtonian gravity has no agency, it's just a law. And objects that fall under the gravitational influence as characterized by Newtonian mechanics have no agency. And when you shift over to either general relativity or quantum mechanics, you find that situation doesn't change. There's no agency. If you climb up towards biology, however, and I've worked with some fairly high-powered biologists in my time, we find that it's very hard to talk about like the immune system or the metabolic system without slipping into teleological language, so language of purpose, right? So the immune system is defending, has the purpose of, or the function of defending against invaders, right? That's a very natural thing to say. And if you were to go visit your physician and your physician used agency-free language to describe your treatment or your diagnosis, you would be really creeped out. So the question is, where does agency sneak into our architectural stack? And what I want to argue is that it should come in at the bottom. It should come in right at the foundations of mathematics. I have a whole other talk that I gave as a keynote at the HDC Eclipse conference in Eugene, and that's online, and you can go see more of that. But here, I just want to, because we have so much content to cover, I just want to dive in and kind of give you some intuitions about what a theory of agency would look like. So the first thought is that agents are not complete. They sort of need to live in a world of exchange. So agents need to be able to receive information from the outside world or other agents, and also need to be able to send information to the outside world or other agents. Right, so that's kind of core to what agents do. And then just to sort of make things complete in a different way, we should also think about agents that do absolutely nothing, right? So agents that have a sense of stillness or emptiness or silence. And that's really kind of the ground on which we're going to build the rest of our notions of agents. There's another interesting twist, which is that we should, in the sense of compositionality, we should think of autonomous agents as being able to be a single agent, right? So that's kind of, all these characters that are tugging on the rope, they're acting in accord, in concert, as one agent pulling on the rope, but each of them are autonomous, right? And this is a bit of a mind twist, I think. We find this as a little bit of a sort of a dark spot in our vision. This idea of compositionality, but it is very important. If you look at the legal system, Citizens United was a big transformation in U.S. law, where it began to treat corporations as if they were individuals. So there's a lot of consequences to this notion that we have to think through carefully. And then there's another important trick that agents have, which is this idea of being able to see the world both as code and as data. And this is a trick that has, in my opinion, this is a hypothesis I would like to submit to you. It's a trick that I think sort of underlies two magical moments that are recorded in the geologic record. So if you look in the geologic record, you find that there's a transition from Earth with no life to Earth with life. And currently, there are no accepted explanations of that transition. There are lots of people who are working on theories, but the scientific community as a whole would agree we don't know what that transition from non-life to life is. Some interesting folks are working on this: Sarah Walker, Lee Cronin, Eric Smith, lots of people, but still we don't have a good theory. Likewise, there's this transition from Earth with life, but no mind, no recognizable mind, to Earth with life with mind. And again, we don't understand that transition. And I want to argue that those two transitions are like each other. There's something similar to both of those transitions, and that at the core of those transitions is this trick of coding, right? So biology today, you can see that sequences of CGAT code for certain proteins. Likewise, the mind has this trick of being able to represent things in terms of abstract representations, which can then be unfolded back into methods or procedures. So that's what's going on in the rho-calculus. So the rho-calculus is teeny tiny. There it is on the page. There's a few equations that I've left off, but they don't make it much bigger than this. Rather than read off from here, I'm going to relate them back to our pictures. So processes, so you can think of them as programs or processes, and we're going to use P and Q to range over them. So a process is of the form, it's either it's the process which does nothing, except for provide stillness and emptiness. Oh, and I should note that the vertical bar in this, when there's space, it means alternatives or. And when there's no space, like here, it's parallel composition. And I apologize for that notational collision. That's the way it's done in the literature. And if I changed the notation, then when you went back to the literature, you'd be a little confused. But anyway, okay, so there's the process that does nothing. And then there's the process here, which is receiving. And then there's the process here, which is sending. So this one waits on some channel for some message, say Y, and then does the process P, in which everywhere Y is mentioned in P, it becomes whatever the message was. And over here, we're sending a message on the channel X, and the only kind of messages we can send are processes. And then this is the parallel composition of two agents. So this is like this notion of autonomous execution. And then this is the coding trick. So the real mind twist in the rho-calculus is that channels are just the codes of processes. And since they are codes, we can take the code and start running it again. And so this pointer notation, for those who have done C programming or other kinds of programming, this is intentionally referring to that sort of thing. And then so that's the syntax of agents. And then the execution model is just that if I have an agent, a process that is waiting on X for some data before it starts running P, in parallel composition with a process that's sending some data on X, well, that just transitions to P, in which everywhere that Y occurs, we substitute the code of Q, where Q was the message. Hopefully that makes sense. Feel free to interrupt if you have questions. But let's do a quick coding exercise, just for fun. And this kind of sort of exposes a lot of interesting things about the rho-calculus. So first of all, we can code up namespaces, right? So anyone who's done real coding knows that namespaces are what kill you in programming in the large. And most programs, programming languages or other kinds of models of computation kind of fluff that off until the end. Say, okay, we'll figure that one out at the very end, and that makes development miserable. Here, namespacing is core to the model, so I'm just going to describe a little function, right? So this is outside of rho. You could write it in rho, but just for the sake of time, I've just written it down in a simple way. So what we're saying is that this function takes an integer and it produces a name. So the name that we're going to get if we supply 0 is just at 0, and we can see that since 0 is a process, at 0 is a legal name. And then what we're going to do is we're going to form a process for for the integer n, we're going to form a process that uses the name at n-1 and sends the star of the name at n-1. So that's a process. So we're sending that on this name, and we're going to take the name of that, right? So it's a little bit tricky, but not super tricky. And then we're saying that the namespace in space is just all of those names for all of the natural numbers. And now I'm going to define a process pi, right? So this is the process that we get if we supply some integer I. And all it's doing is it's going to listen on the name at ni, and then it's going to send whatever it got on ni+1, and then go back to being itself. So basically, it's just a little forwarder. I get it on the ith name, and I send it to the ith+1's name. Nothing fancy about that. And then we're going to have p be the parallel composition of all of them, right? So you could think of this as an infinite parallel composition. Now, what happens if we send a process q at, say, nj, and under the influence of p? So it's running together with p. So what we'll see is that it acts like a force on q. It whisks q off along the line of one location in n space per communication event, right? So these are called communication events. So this looks very much like a physical force. And in fact, we can go quite a bit farther with this analogy. I don't have time to do that here, but you could imagine that instead of whisking it off at 1 per comma event, we could whisk it off as the square of the comma event. So we could, and in fact, we could represent acceleration and many other physical phenomena that are related to gravitation. So this gives you some sense of how we might model the physical world using rho-calculus programs. So now I'm going to switch gears, and I'm going to talk about the ZX calculus. But before I do that, I just want to point out that the big trick here, right, in terms of our theme, is connections. So agents are programmed using channels, and these channels are connections between agents. And here, what I was saying before about the rho-calculus is that connections are entirely programmable. That's what's going on here. We're saying that a connection is just the code. A connection is code, right? And if you look at our example, here we're using codes to write down this whole giant infinite network of connections. And each of these codes is providing an important role with respect to modeling of a physical force. The role here that they model is they're providing a coordinate system. So we can build a namespace that's like a coordinate system. Now, when we go to the ZX calculus, here's the ZX calculus on a single page. There are variants of the ZX calculus. I don't expect you to grok this page all at once. We'll dive into it. But the answer, so Ross Duncan and Bob Kuka sort of asked the question, what's special about quantum? And lots of people have provided different answers, right? So a lot of people say what's special about quantum is this idea of superposition. It turns out that that's not true. You can code up superposition in classical systems. In fact, as I was doing the literature review for hyperdimensional computing, there's a researcher who's done who's used hyperdimensional computing, the sparse dense representations. I'm sorry, the sparse distributed representations, to code up a notion of superposition that's extremely fast in a classical setting. So it's not superposition. I won't go through the list of all the things that people have proposed that are special about quantum, but what Bob Kuka and Ross Duncan, who discovered the ZX calculus, propose is that what's special about quantum is complementarity. And you'll see that's kind of why there's red stuff and green stuff in these diagrams. They represent complementary orthonormal bases. So it turns out that an orthonormal basis allows you to do things that you can't do in just an ordinary arbitrary linear so with some arbitrary linear representation, you can't necessarily copy, right? So everyone knows there's the no cloning theorem and the no deletion theorem in quantum mechanics, right? So that's a well understood. But it turns out that if you do have eigenvectors, you're perfectly free to copy and erase. And so this notion of being able to copy, so that's kind of what this delta represents, duplication or copying. So data comes in and two copies come out. And then this is erasure. So data comes in and nothing comes out. And then dual to that, if we just flip these upside down, we have a notion of multiplication. So I can kind of take two datum and combine them and get something out, right? So like adding numbers or multiplying numbers. And then I have a notion of a unit, right? So I don't need anything to produce the one, for example. It turns out that an algebra like this that obeys certain laws is called a Frobenius algebra. And it coincides exactly with the notion of observable. It coincides precisely with an orthonormal basis. And what the ZX calculus says is that we're gonna grab a couple of these algebras, so a couple of Frobenius algebras, and notice down here that I flipped the order, right? So instead of having the duplication and the erasure over here, I put them on the right, and the multiplication and the unit are on the left. And the reason is because when we bracket them this way, they form another kind of algebra, which is called a Hopf algebra. And you don't really have to understand what this is, other than to understand that it provides some identities with respect to these operations, which we can look at here. So, for example, when I have something wired up this way, when I have one of these diagrams wired up this way, I can turn it into a diagram wired up this way. When I have a red unit wired up to a green duplicator, then I get to push the duplication through. This is one that in Ross Duncan's introduction to ZX calculus, he describes it this way. There's no real communication. This equation says there's no real communication across two different orthonormal bases. So again, I neglected to mention something super important. Apologies, which is that you can think of the green as representing the Z basis, and so that's the 0 and 1, and the red as the X basis. So that's normally written as the plus minus states. So what we're saying with this equation is that whatever's coming in here, even though they're wired together, there is no transmission of information, and that's really what's coming from from one of the important things that's coming from the fact that these two Frobenius algebras are kind of connected by also being Hopf algebras. And now what can you do with the ZX calculus? Well, here's an example I stole from Ross Duncan's talk. One of his undergraduate students did a basic error correcting code. So here we have 3 qubits coming in, we have 8 qubits coming out. So this is the code word, and this represents a particular way of doing an error correction code. And then so this is the encoder, and this is the decoder. So here, the decoder takes in the eight qubits and gets out 3 qubits, right? So I'm sure everyone is kind of familiar with the idea that quantum computing is noisy, and so error correcting codes are very, very important. And you can use these ZX equations, so these, to rewrite this to show that they end up just being wires. So what you get in, you get out, right? So it does its job. Now it's 4 pages of rewrites. So it's somewhat complicated, which is why I didn't write them out here, because we don't really have time. Certainly you can go find the paper for this. The important point is that there are already theorem provers for ZX, like Quantumatic, and then there's another system called PISX that automate a lot of this rewriting, so that you don't have to do these kind of error-prone things. And in fact, in general, what we find is that the quantum circuit notation is extremely error-prone because we don't know. It gets very complicated very fast. There are lots and lots and lots and lots of different identities that we could impose. We don't know why, to pick one collection of identities on quantum circuits versus another. All the quantum circuits can be encoded in ZX. In fact, ZX is complete for linear maps. So in particular, two diagrams are equal in the rewrite sense if and only if the linear maps they represent are equal. So there's a completeness, and in fact you can represent all linear maps that way. So that's quite an endorsement for the expressive power of ZX. But ZX, as I mentioned, has just a handful of identities, and we know exactly why we get those identities. These identities come from I'm sorry, I skipped over it. Whoops. They come from the fact that we've got these 2 Frobenius algebras that are complementary and interacting. That's where they come from. Now, there's a bunch of other stuff I'm skipping over that's worthwhile if you're interested in the ZX. Like, for example, this one, this yellow H box represents the Hadamard gate. You can encode the Hadamard gate in ZX, but because it's used everywhere, the Hadamard gate, it's easier to make a macro for the Hadamard gate, and then we can see exactly this complementarity, right? If you surround a green dot, a green, they call them spiders, with Hadamards, then you can turn it into a red spider. So that's how you turn them back and forth. And there's a bunch of other stuff to explore, but I thought we might explore it in a different way by looking at the connection between the ZX calculus and the rho-calculus. Before I do that, let me stop again and check and see if there are any questions. It also gives me a chance to take a sip of coffee. Okay. Well, I haven't heard anyone chime in, so let me quickly dip our toes into what might be the relationship between the ZX calculus and the rho-calculus, and this gives us a little bit more of a flavor for what's going on with the ZX calculus and what makes it special. So naively, if we look at a spider, I would prefer to call them chips or something, because spiders don't typically have M legs on one side and N legs on the other. But Bob dubbed them spiders, and the name has stuck. You can think of spiders as representing some component in building up linear maps that's quite useful. So one way to think about this is, so for each of these, I'm going to treat these wires really as if they were channels. And so we have Z input channels and Z output channels, which I've denoted here, Z minus and Z plus. And so essentially what we're doing is, to represent this thing, we're saying, well, we're going to listen on the z minus 1 through z minus m, so that's m of those, right? For some vector, and then what we're going to put out on the z output channels 1 through n are e to the I alpha. There's the phase right there, multiplied by the by what we got. Oops, there's a little issue here which I'm going to gloss over for a minute. You could probably see what the issue is, but anyway, so the question is how you map from m to n. So there's a little bit more that needs to be done here, and this is just listening on the X channels and sending on the X channels. So the question is, if I'm going to wire a green spider to a red spider, which I can do, how do I get the Z output channels connected to the X input channels? So here, the idea is that we have 4 different kinds of processes, right? So I can have a Z wire which listens on a Z output channel and sends to a Z input channel. So that connects green to green. And likewise, I can connect X to X, right? I can listen on an output channel and send to an input channel. So that would allow me to connect X spiders to X spiders. Now, the point of the hop, this thing here suggests that maybe one way to think about wiring red to green is that I can't really transmit. So what I transmit is noise. And then when I would compose this way, right? So I would go translate. So if I'm wiring up D1 to D2, an X to an X, so an X, the ith output to the jth input, then I would close up over that position. So that's what this new is doing. It's saying this is a fresh channel and it's hiding the channel from the outside world. So something can't sneak in and listen on that channel. And then I would take the translation of D1, put it in parallel composition with wire X. So that would be this one, and this should be the IJ, right? And then the translation of D2. And similarly for the rest of them. So hopefully that gives you a sense of both, the information flow intuitions of the ZX calculus and how we connect that information flow intuition to the rho-calculus. So there are a couple of more ZX diagrams, which are cup and cap, and these are particularly interesting. To me, this is one of the things that makes it super. This makes quantum computing special from the point of view of information flow, in my opinion. So in particular, here you have 2 inputs and no outputs, and as a result, it's quite challenging to say, what the input might be, right? So we can't really. It's very hard to say what the signal is in this case, right? Because and it's even harder to say what the signal is in this case where we have 2 outputs, right? What signal are we outputting? In this case, we can kind of say, well, whatever signal we get over here, it needs to be the same as the signal we get over here. And that's really what's going on with cup. But in terms of cap, it's much harder. So here, what we do is we do a sum. So I didn't use summation or plus in the original presentation, but there's a way to think about this as non-deterministic sum. So there's a bunch of copies of this process, one for each y state or y vector. And only one of the copies is going to go, and that copy is going to go in the case that both on x1 and x2, we see a y. And here, what's going on with the cap is I'm going to close up over the x minus. I'm going to send a y on the x minus, pick it up here, and then send that y out on the x1 and x2. But I'm going to do that over all the different y's. And so now there's an equation that we would have to verify, which is that if we wire up a cup and a cap, is it actually a wire? Does it just send signal through? Now, in this particular case, it does, and it's really quite tricky to see it. One way to think about it is, suppose that that one of these y's wins. There's some non-determinism here, right? This could ping, because this is available to the outside world. This could win, and then force some information flow this way, or this could win and force some information flow this way. If this wins in this racing with respect to the outside world, then what will happen is the Y will be selected by the output, and as a result, X1 and X2 will both be Y. Now we've wired up X1, this one, to X2, which is this one, which then forces this to be a Y, because the only way this will ever go is if both of these are the same Y. And then and that means that the only way this will interact with the outside world is if the outside world is sending that Y. So what that means is, if we get a Y on this side, the same Y will be on this side. And likewise, if you run it this way, if we get a Y on this side, that forces that the only thing that we could do down here is a Y. So it does act as a wire, but in an extremely complicated manner that is quite difficult to implement from a classical point of view. So in my opinion, this is one of the things that's quite special about quantum. And in fact, if you go understand what cup and cap are doing, they're closely related to the Bell state and the Bell measure. So yes, there's something about non-locality going on, and this is closely related to quantum teleportation. So absolutely, there's something special going on here, and doing this kind of information flow analysis allows us to see it quite clearly. All right, let me just check the time. What time is it? Okay, we've got about 15 minutes. That's just enough time to do about 5 minutes of HDC, and then 10 minutes or so of questions. I might split it down the middle, so 7 minutes here and then 7 minutes of questions. So in the same way that we give a kind of grammar and execution mechanism, I'm giving a similar presentation for hyperdimensional computing. So the idea is that I'm going to build these extremely large vectors. So think, thousands and thousands of components in these vectors. And the individual components, for our purposes, they're going to be bits. So either 0 or 1. They can be other things, and people have explored what those other things are. In my opinion, I haven't yet proved this, but I'm fairly confident that that we can shift to saying that what's in the components are elements of a quantal. So a quantal is a particular kind of lattice-like structure, having that ability to abstract what goes into the components of each vector is important for compression. So if I run out of space in my compute to do with just bits, I can bump up to a quantal that has richer richer information content in each of the elements rather than 0 and 1. So for example, I don't know, the complex numbers, which would then relate back to the ZX calculus. That gives us the ability to do more compute with the same total number of vectors. But anyway, so I've got these large vectors, they're filled with either zeros and ones. A way to think about how we can build them is just in terms of this instruction set, right? So a vector is either the 0 vector, which is 0 in every component, or the 1 vector, which is 1 in every component. Or think of this as a null array function, right? It takes no arguments and it produces a vector. And so that's what this type is here. No arguments, produces a vector. And that vector is a random vector drawn with the Bernoulli distribution. That means half the bits are on and half the bits are off. And then the rest of these are fairly straightforward. There's one that's a little bit different. So here, what we're going to do is do a component-wise XOR. So that's what I've written down here, and then you can see why I suspect that we should be using a quantal, right? So if you have a quantal, then you have a join and a meet, and when you have a complete lattice with an implication, and you can imply to the bottom element you have a negation. So all of these operations would be available in certain kinds of quantals. And so this is again, it's just component-wise XOR. Permutation is just what you might think it is. It switches around some of the components in a vector. Now the way we write it here is I'm gonna treat the first vector in the permutation argument. So permutation takes 2 arguments, right? Both of them are vectors. I'm going to treat the first vector as if it were code for some permutation, right? So if n is the dimension of our vector space, then this is the group Sn, right? It's an element, and so what we do is we go figure out what permutation that is. That's what this, bracket pi is, and then we apply that to the second argument. And so if we want the jth component of the permutation, this is how we calculate the jth component. And then majority sum is given by so I have in vectors coming in, and to get the jth component of the majority sum of those in vectors, it'll be 1 if I go look at the jth component of each of the vectors, and if the majority of them are 1, then it's 1, and it will be 0 otherwise. Now, if there's a tie, you have some kind of tiebreaker rule, and it doesn't matter all that much, which you can flip a coin or whatever. Now this turns out to be Turing complete, but I want you to notice that this is just a data model. There's no control flow here. The data model is rich enough to code up a universal machine, but it doesn't say who calls the operations on this data structure, when or under what conditions. That's quite different from the 2 models I presented before, right? So HTC, despite all of its wondrousness with respect to training and learning, it doesn't have a control flow model, right? So this slide is just reiterating what I said before, but from the perspective of connectonomics, right? So you can see that each of these operations, can be viewed as, in some ways, a lot like the ZX spiders, right? And the way we do compute is by wiring up these combinators, or these spiders, so to speak. But again, there's nothing in the model that's telling us when to wire what to what. And there are no, in other words, there's no rewrite rules here. Now, it turns out that you can find some rewrite rules. We're running out of time here, so I'm going to I'd like to go deeper into this at some point, but if you want more depth on this, I would recommend my HTC Eclipse talk. But the trick, at the high level, the trick is that we extend this thing with some syntax. So we're going to import all these vectors as vectors in the syntax, right? So these are constants in our programming language. Now we have an instruction called rand. It's not the same as this operation here. This is just a piece of syntax. We have an instruction for XOR. It's not the same as this. This is just a piece of syntax, and so on for the other operations. And then we can build a compiler that takes in something in here and produces something in here. And what that does is it allows us to see some of these things as if they were code, right? So we're teaching HTC the trick that nature learned a long time ago. And the rest of this slide is just saying how you do that. So it turns out that rand is dissimilar from all other vectors. So you can treat rand as if you're generating symbols. So you can generate symbols for each of the term constructors and generate symbols for the accessors. And then what we're doing here is there's a trick to coding things as records. So when we have an XOR, we label it as an XOR, which we can do with the actual XOR operation, right? So this is the symbol XOR. We're XORing it. So this is a vector. We're XORing that vector with another vector that depends upon the code of each of the components. And the way we get that is we go figure out the code of each component, label it with left and right, and then take the majority sum, and then we XOR that with the label. And the same is true for the rest. And then it turns out we can lift, we can create a rewrite system, which will just evaluate code. So it gets a vector in, it recognizes that the vector is code, and then actually runs the operation that corresponds to that code, right? So, but that turns out to be miserable from the point of view of programming. So what we can do is we can add, let's see if I can, that's probably too small to read. Normally when I give this talk, I just show that you can do the same trick and adding the lambda calculus as extra syntax. And then this is a compiler for the lambda calculus down to HTC itself. Again, we're just doing the same trick we did before, except now we have to handle substitution. And then we can do the same thing with the rho-calculus, where we're just extending the HTC syntax with the row terms, and then we have a compilation method down to the rho-calculus. The one thing is, in both of these pages, you'll note that there's something funny going on here. What happens here is we go back, we pull back the vector into the lambda representation or the row representation, do the substitution, then turn it back into row. Now that's not what you want to do in an implementation. In a real implementation, it turns out that you can shred a piece of syntax into paths from the root of the syntax tree down to the leaves, and then form two tables. In the table, in one table, the path is the key, and what's at the end is the value. So the values will either be constants or variables, and then the other table is from variables to the paths that they're the values of, and then you can use just hypervector operations to do substitution. So that's basically what this slide says. So I'll stop there. It still gives us time for questions. But really, the heart of this talk is that it's all about the connections. It's all about reasoning about the wiring. And all three of these models, which are changing the way we think about computation. So the rho-calculus changes the way we think about concurrent and distributed computation. The ZX calculus changes the way we think about quantum computation. And hyperdimensional computing changes the way we think about learning. All three of these models, the strength of the models is that they they have provided a different way of thinking about the wiring of things. So with that, I'll stop and take some questions. Surely somebody has some questions. I know I didn't explain everything perfectly lucidly.
Joe Reddix?
Lucius, I got a quick question. It's related to photonics. You know, I'm looking at your connection, the capability, and I can understand it, but how would it relate to photonics? Would it be? So go ahead.
That's a great question. Thank you so much for that. It turns out that a variant of the ZX calculus called the ZXW calculus, where you have an additional basis, is being used extensively for reasoning about photonics. So if you follow Bob Kuka on Twitter, you'll see that he's frequently talking to the photonics labs. So if you're interested, look at the ZXW calculus. And again, the moral of the story is it's all about the connections, right? So Bob's slogan in his original paper is only the topology matters.
Okay. Thanks a lot for that.
Sure.
I guess I can do a follow-up unless somebody else has a question. What I was looking at with that particular question was developing a strategy between classical and quantum computing. You know, the reason why I say that, because it looks like the hybrid strategy is going to be the next step in marrying classical, whether it's exascale or whatever, classical perspective to quantum. Now, looking at your, sorry, go ahead. Sorry.
No, I'm sorry. I didn't mean to cut you off, but so originally I had wanted to also talk about the notion of hybrid because, but I just realized I had so much material I had to kind of cut it off. So each of these different models, but especially Rho and ZX, have different ways of talking about hybrid systems. So it turns out for the rho-calculus, there's a way to also interpret this from a quantum perspective. So rather than trying to code ZX into Rho, we can enrich the COM rule in such a way that basically, roughly speaking, you can think about decorating the channels with rates, and if you just decorate them with real numbers, you get a version of Gillespie, which allows you to do stochastic simulation. If you decorate them in such a way that the probability distribution is a probability amplitude, right? So you're decorating the rates with complex numbers. Then you get a quantum style execution, and so then that gives you a calculus that allows you to reason about end-to-end hybrid systems, right? So some systems are classical protocols and some are quantum protocols, and you can express it all in the same language. Now, Bob likes to point out that you can also you can think of these diagrams as classical, and then the quantum version of them is just you double everything. So ZX calculus also gives you this ability to reason about hybrid systems. It's going to be interesting to see how, in my opinion, this is much easier for reasoning about classical protocols, whereas this is somewhat easier for reasoning about quantum protocols. So I believe that somewhere in between the two is how we're going to reason about hybrid systems. But that's still to be determined. But thank you for that question, because that really was what I was hoping to talk about today. But there's just too much material to go through to get an understanding of all three of these models all at once. Great question.
Thanks a lot.
Yeah. Any other questions, comments?
if there are no other questions, I just want to
And a
say,
copy
Greg,
of the deck.
Go ahead.
yes, we will, I did access the deck, so we do have that, and I can send that out along with the, a recording of the session, so that will be available to everyone, so. But Greg, thank you so much. You know, I am not a mathematician, but I am glad there are people out there like yourself. Very grateful, so thank you so much.
No, thank you. Thank you. I had a really good time giving the talk, and I had a really good time preparing it. It was a lot of fun.
Fantastic. We hope to have you back.
Like, I would love to be back. Have a good rest
Fantastic.
of Wednesday, everyone.